we'll talk about several ways in which we can slice the two-input production frontier and get meaningful economic concepts. The first of these is to slice the production frontier horizontally, which we'll do in this animation. We begin by drawing a three-dimensional production frontier where labor and capital are the inputs and output is denoted by X on the vertical axis. This production frontier is a hollow mountain that tells us the more inputs we use, the more output we're going to get. The production frontier, together with everything below that hollow mountain, then forms the producer choice set. We can then find all the different ways in which we can produce 20 units of the output by slicing the production frontier at the height of 20. Similarly, we can find all the combinations of labor and capital that can produce 40 units of output by slicing the production frontier at the height of 40, or all the combinations that can produce 60 units of output by slicing the production frontier at the height of 60. The magenta slice, for instance, then lies on a plane that emanates from the vertical axis at 40 and is parallel to the horizontal plane denoting labor and capital. Stripping away the rest of the production frontier, we can see the three slices hovering in the air at the three different output quantities 20, 40, and 60. We can then project these slices onto the horizontal plane that contains labor and capital and label them with the height at which they appeared in panel A. Straightening this out, we then get a graph of what we call isoquants. These isoquants represent different ways of producing different levels of output using different combinations of inputs. All the input bundles on the blue isoquant represent bundles with which we can produce at most 20 units of output. Similarly, the magenta isoquant represents combinations of labor and capital with which we can produce at most 40 units of output, and the green isoquant represents combinations of inputs that will result in at most 60 units of output. A point like A can then be interpreted in two different ways. Strictly speaking, point A is an input bundle, the input bundle that contains 20 hours of labor and 10 units of capital. But when we combine it with the label on the magenta isoquant, we can also say that A represents a production plan. It represents the production plan that tells us to use 20 hours of labor and 10 units of capital to produce 40 units of output. We can then write A as the combination LK equal to 2010, which views A as an input bundle. Or we can represent it as XLK, the production plan, that contains 20 units of labor, 10 units of capital to produce 40 units of output. If you're using the calculus-based book and you've read part B of chapter 4, you've already encountered a very similar graph in graph 4.8. Alternatively, if you're using the non-calculus-based book and if you looked at the Exploring Relationships animations under chapter 4, you've also seen a very similar animation already. In those animations, we derived the indifference curves for consumers from a utility function, or what we call the utility mountain. Deriving such indifference curves from utility mountains is in fact very similar to deriving isoquants from production functions. There's one important difference, however. When we talked about the labels of indifference curves in consumer theory, we said that those labels didn't have any inherent meaning. The only reason we labeled indifference curves was to indicate which indifference curves are more preferred and which are less preferred. This was because we didn't think that you could measure utility objectively, and certainly not in a way that makes it easy to compare utility units across individuals. Here, however, we're measuring output, and output can be objectively measured. So the labels on the isoquants, 20, 40, and 60, are objectively measurable quantities of output, and therefore have real meaning in the way that labels on indifference curves did not.